All right, so we're at the last section of the chapter, and we're going to cover in a very kind of condensed way a couple of really important topics that I'm sure are going to come up again and again later in the book. So you'll get lots of practice with them. And here we'll just kind of cover some of the basic definitions and some of the key properties. And these topics are relative entropy, which is also known as Kullback-Leibler divergence, a way of comparing probability distributions, and mutual information, which is a way of measuring the dependence between two random variables. So really important, and we'll just kind of touch on them here, just enough for that we'll need for the rest of the book. And I'm sure you'll get lots of practice using these as we go through the book. So now there's a lot happening, as I said, in this section. And in fact, so I thought it might be useful to actually split this up into the various sections and kind of mark them out as we go. So the very first section here is this one, and this is just defining, the KL divergence. So we'll talk all about that briefly and kind of motivating it in a very interesting way. Then we are going to talk about a property, one of the really important properties of this divergence, which is that it's greater than or equal to 0, and it's only equal to 0 when the two distributions are equal. So we'll see what that means. It's a really important property, but to actually be able to prove that, he introduces the notion of convexity that he's going to use to prove that property. I've already made a video about it. Actually, the last video was about that. So if you haven't seen it, go check that one out. But once you've kind of covered convexity, then we get to this important result here. So the fact that the Kullback-Leibler divergence is greater than or equal to 0. So that's kind of the next little chunk. So it'll kind of stretch on all the way to here. And then he'll kind of talk about the kind of summarize the discussion, which is kind of the connection between data compression and density estimation. And then there's a section here now, which again I think is also really cool. So this is the connection to ML estimation, maximum likelihood estimation. So how Kullback-Leibler divergence ties into that. And then finally, at the very end of the chapter, we arrive at this notion of mutual information. So, and how we can define that using this Kullback-Leibler divergence. So there's a kind of a lot going on in the chapter. So I just wanted to kind of mark out those sections, and they're, you could probably go on, for a whole chapter on each one of those. So yeah, hopefully that'll help. And now let's go back to the top and start discussing it. Okay. So let's begin. So we've introduced, so in this chapter, in this section, we introduced a number of concepts from information theory and this key idea of entropy, right? So that was kind of entropy was like the average surprise, about the values of a random variable. So now we're going to relate these to pattern recognition. So now he says the setting we're going to be in. So as I've been mentioning so far, the relative entropy, Kullback-Leibler divergence, and mutual information are ways of comparing probability distributions. So we now have two probability distributions. One of them is going to be some unknown one, and one of them is going to be an approximating distribution. So we're typically trying to model this unknown thing with something that we have a kind of a good control over. Maybe it's tractable, whatever. So that's our kind of Q of X. Q of X is throughout the book going to be used to be the stand-in for the distribution that we sort of have control over. And kind of an example of this would be like, let's say you're interested in like the distribution of heights in the population. We don't know what that distribution is, so you might want to model it with something. So for example, that would be, you might want to model it with like a Gaussian distribution. And so your Q of X would be a Gaussian, and maybe you have some parameters you can tweak. In kind of maybe a little bit more advanced setting, this comes up all the time in what's called variational inference, when you're trying to kind of infer in latent variables. So some, the latent variables of some model, and often the distributions the true distributions over those latent variables in a complex model. For example, let's say what is the probability that there is a cat in a particular video, or the distribution over animals in a particular video. That can often be quite complicated. So you'll frequently need to resort to using kind of a simpler distribution, and then you'll adjust its parameters to best approximate the distribution you're after. So this kind of notion of the unknown distribution and approximating distribution come up all the time, and you want to often compare these. Okay, so now it says if we use Q of x to construct a coding scheme for the purpose of transmitting values of x to a receiver, then the average additional amount of information in NATS required to specify the value of x, assuming we choose an efficient coding scheme, as a result of using Q of x instead of the true distribution P of x, is given by this thing. Okay, so this is there's a lot to unpack here, so let's do that together. So I'm gonna change pens here. So, okay, so we're constructing a coding scheme for the purpose of transmitting values of x to a receiver. Okay, so the idea here is that we want to send some messages. Let's just assume discrete messages. Let's say letters of the alphabet, and we're going to use Q of x to construct our scheme. And remember, the idea is we're using an efficient coding scheme. And if you go back to kind of the lectures on entropy, the idea was that a coding scheme is efficient if the length of xi is going to equal to as close as you can get to ln of 1 over the probability of xi. And so the idea there was you want to spend your coding capacity, your bits, trying to transmit the unusual events. So if something, for example, if you're reporting the weather in Dubai, well, maybe you don't want to use your coding, your channel capacity, the amount of bits you can send to say that it's sunny, right? It'll always be sunny. Maybe that should just be the default message. You should spend zero bits on that, and only signal if, let's say, the weather's started to rain. And so we saw that the way that if you want to transmit information as efficiently as possible using the smallest number of bits on average, then the amount of bits that you should assign, or nats if you're doing things in natural logarithms, should be proportional to the surprise, which is 1 over the inverse of the probability of that event occurring. So if Q is very small, so if that's a very rare event, well, 1 over Q is going to be very large, and you should have a kind of a long code word for that. Whereas if Q is very, it happens all the time, Q will tend to be close to 1, so this number here will be much smaller. You'll be using a much smaller code word. So that's what he means. This is what he's talking about with using an efficient coding scheme. Okay, so we're using Q of x, but the true distribution is P of x. Okay, so there's this causes kind of two terms to show up. So let's look at what those are, and maybe we can zoom in here. Okay, so this term here that's going to be the average. That would be the average length of the number of bits you're transmitting if you knew the true probability distribution, right? This was just the entropy of the distribution, the differential entropy in this case, but the entropy of the distribution. So this is the average length of transmitted if we knew the true distribution, right? Because we are averaging with the true probability, and we're assigning code lengths according to this ln of 1 over P of x. So that's the ln P of x, and the minus is making it ln 1 over P of x. So this is kind of the average length that you would be transmitting, the average length of your messages, if you encoded your code words according to the true distribution. But the idea is that we don't know that true distribution, so we have this other term. So this is the actual, you can think of this as the actual, average length actually transmitted. And now, okay, so now notice a couple of things. So first of all, so this is, we've got the ln Q of x, and the minus, that's coming from we're trying to encode efficiently, but we just don't have the right distribution. We don't have the right probability distribution over the code words. So here is ln Q of x, so that's this thing. But notice that we are averaging with the true distribution of those events. So, for example, we don't know the actual distribution on the weather. So maybe, I don't know, like you're new to Dubai or something. And so you set up a bunch of code words that maybe assign really, long, symbols to sunny. So, the weather is going to be whatever it's going to be, right? So the weather is going to be generated according to P of X, but you're going to be sending, bits according to Q of X. So now this KL divergence is actually the difference between the length you actually send and the length you could be sending. And you can just rearrange this, and it becomes it looks like that. So it's a kind of a difference of these. And now we don't know at this point. It seems like, based on the way I've kind of presented it to you, and what we know about entropy, we would expect this thing to be greater than or equal to 0, but that's something that you need to show. Okay, so this is kind of a nice motivation for this, for the idea of Kullback-Leibler divergence. This in terms of this coding, how much extra you have to spend transmitting a message when you don't know when you're using the wrong distribution, the wrong probability distribution to determine your code words. So that's this. Now, one really important property of the Kullback-Leibler divergence is that it's not symmetric. So you can see that the P comes first and then the Q, and so you can see that P is here, P is there, and Q is up there. If you switch Q and P, well, you will get KL in the other direction, and in general, those won't be the same. So it's really important to remember that this notion is not symmetric. So that's one of the reasons why it's not a distance, right? The distance from A to B is the same as the distance from B to A. Well, that's in general not true for the KL divergence. So something to keep in mind. Yeah. Okay. So the next thing he goes on to talk about is this important property. So there's actually a couple of important properties, which he actually states here. So the first is that the KL PQ is greater than or equal to 0. So it's always positive, as kind of that motivation suggested. But then with equality, if and only if P of X equals Q of X. So you can imagine this thing being, okay, like maybe it's greater than or equal to 0, but maybe the averages work out in particular cases in such a way where I can have the wrong coding, the wrong coding distribution Q of X, but somehow get a KL distance of 0. It seemed kind of intuitively unlikely given the motivation we produce, but maybe it's possible. But it turns out that actually that doesn't happen, thankfully. So the only time that you will get KL being equal to 0 is if the distributions are exactly the same. And that's why it's actually useful. That can be useful it can be used as a measure of dissimilarity between distributions. So it will say that the value will always be positive and will be 0 only if the two distributions are the same. So you can use that to measure, how similar one distribution is to another, and not have to worry about getting spurious cases where you get a similarity, a dissimilarity of 0, telling you that the distribution should be identical when they actually aren't. So this is an important property. So in the next section, he kind of introduces the notion of convexity that he uses to prove it. We've already discussed convexity in a previous video, and I'm going to make a separate, in the next video, you'll see, I'll actually prove this, this property using these notions of convexity. So for now, we'll actually go and prove this thing together, at least for the discrete case, in the next video. So for now, just take that to be given that the KL divergence between two probability distributions is greater than or equal to 0 with equality if and only if P is equal to Q. Cool. So, and yeah, he ends up just saying, let's switch to, hopefully you didn't miss too much there. Yeah, so he says, look, we can interpret the Kullback-Leibler divergence as a measure of the dissimilarity of the two distributions P of X. So that's, again, because the equality, KL P to Q will be equal to 0 if and only if Q of X equals P of X for all of X, if the two distributions are the same. Great. Okay, so then he kind of summarizes that discussion in kind of a nice way, and he says, look, what we've essentially just seen is that there is an intimate relationship between data compression and density estimation. So data compression is, assigning, different length code words, different length symbols to messages you want to send. So what's the best way of doing that to, to avoid sending unnecessary bits, basically. And then density estimation is just knowing your probability distribution. So what the KL divergence tells us effectively is that the most efficient compression is achieved when we know the true distribution. So whenever you don't know the true distribution, when Q doesn't equal to P, your KL is going to be positive, meaning that you'll be sending extra bits. If we use a distribution that is different from the true one, then we must necessarily have less efficient coding. So that means sending more bits than you have to. And on average, the additional information that must be transmitted is at least equal to Kullback-Leibler divergence in the two distributions. So it's at least because, like the efficient coding requires you to be able to make, let's say symbols that are, they can have like fractional lengths and things like this. So on average, it'll even be longer than, the difference will even be longer than what the KL tells you. But the KL is kind of like the lower bound. And if that lower bound is positive, it means that you don't have the right distribution. Okay, so that's kind of the end of those two sections. And now in the next part, we're going to talk about the connection of Kullback-Leibler divergence to maximum likelihood estimations. And I think that's also kind of a really interesting perspective and kind of gives some additional insight. So it says, okay, suppose that data is being generated from an unknown distribution P of X that we wish to model. Okay, so like let's say the distribution of faces, right? So you have a bunch of pixels and you want to know the distribution of the various pixel values for for faces. We can try to approximate this distribution using some parametric distribution Q of X given theta, governed by a set of adjustable parameters theta, for example, a multivariate Gaussian. So you can imagine that your distribution of like photos of faces, there's going to be some mean pixel value for each of the pixels, and then some covariance of how those pixel values relate to each other. So obviously that's a very simplistic model of faces, and it won't capture lots of things about it, but it might be enough for in certain settings. Okay, so governed by a set of adjustable parameters theta, for example, a multivariate Gaussian. Okay. So now it says, well, now we've got this tool, right? We've got P of X, and now we've got Q of X given theta, and now we can say, well, let's try to make Q of X given theta close to P of X, right? If we knew P of X, we could do that by just minimizing the Kullback-Leibler divergence. So it says one way to minimize theta is to minimize the Kullback-Leibler divergence between P of X and Q of X given theta. We probably won't be able to get it to 0, but maybe we can get those, just those theta so that the distance is as small as possible. Now we cannot do this directly because we don't know P of X, right? Now imagine like that would just be very difficult. However, suppose, however, that we've observed a finite set of training points. Suppose we've actually got a bunch of pictures of actual faces. Then the expectation with respect to P of X can be approximated by a finite sum over these points using 1.35, so that we get this. Actually, let me highlight this important expression, approximation to the KL divergence. Let's see where this comes from. So it comes from, let's just do this quickly because it's pretty straightforward. I'll just zoom in. Okay, so let me just, yeah, there we go. Okay, cool. So the idea is that I'm just adjusting this so you can see. Okay, so the idea is that KL of PQ is going to equal to, it's this average P of X of, log P of X over Q of X dx. And now his point is that, look, we don't have P of X, right? So we can't actually compute this average. So how are we going to minimize that distance? So the idea is that we can approximate this average. So you'll remember that let's say you have some function. Let's not get into that. So essentially what we assume is, suppose that we can sample xi's from P of X, right? and that's kind of, that means like it's the same as we've actually got some pictures of faces. So now what that means is that we can actually approximate this this term that we're trying to average. And we're trying to average this term over here. That's here's the p of x, and we're trying to average this by just adding up the corresponding terms for the samples that we have, and then dividing by 1 over n. Right? So what he's essentially saying is, if you have n samples, you can actually write this as 1 over n of sum I is equal to 1 to n of log p of xi over q of xi. Okay, so that's all it is. So he's saying that, look, we can't. We've got this big, we've got this big integral that we need to compute. We can't actually do it because we need p of x. So now, barring that, well, what we'll do is we'll just sample. We do have samples. We have some training samples, and so we'll just approximate this, this average, by averaging over the corresponding values for our samples. So we're just taking the xi's, we sample from p of x, and now we can compute this quantity, and now we average. Okay, so now you might be complaining that, well, okay, so sure, but I thought we didn't have p of x. So how am I actually going to compute the probability of p of xi? Like, that we've essentially solved one problem. So we've solved the first dependence on p of x, but p of xi is showing up again. So so what happens there? Well, the important point is that actually the theta only shows up in the q term. So essentially what we do is we can just write this as 1 over n sum log p of xi minus log q of xi, given theta. He called it x of n. And now we're going to be just optimizing over theta, right? But there is no theta in. The theta only shows up in this term. It doesn't show up in this term. So that means that we don't actually have to worry about this ln of p of x of n, because as far as our theta is concerned, we just need to optimize q of x of n given theta. So despite the fact that the probability of in this approximation, the probability of a particular training example comes up, as far as our optimization is concerned, let's say I'll kind of write it out. We'll say we're looking for theta. Let's say we're looking for theta dot is equal to arg min over theta of q, where q, maybe there's a theta in here showing up in there. Well, as far as that minimization is concerned, these terms, they don't really matter. So we can, this procedure of trying to make the KL, make the KL distance divergence smallest between our approximating distribution and our true distribution, we can do that without having to know the true distribution. And when we actually do it, it ends up, what we end up optimizing is this term here. And this term looks like, you want to minimize this negative logarithm, which is the same as maximizing the logarithm. So this looks like maximum likelihood estimation, where you have a bunch of independent samples and you are maximizing the probability, the likelihood of your parameters given this distribution Q and these particular samples. So essentially all he's saying here is that minimizing the KL divergence in this approximate way brings you back to maximum likelihood estimation, which I think is pretty cool. So what he says is, we can, suppose you observe a finite set of training points, then the expectation, so remember, like this expectation here can be approximated by a finite sum over these points, using 1.35, so that, as we just derived, the KL is this. There's a factor of 1 over n missing, but it doesn't really matter as far as the optimization is concerned. And it's equal to approximately because we are replacing this integral, this average, with our average over the samples. The second term on the right-hand side is independent of theta. So this guy here, yes, it shows up in the formula, but we don't actually need it when we're doing the optimization. And the first term is a negative log likelihood function for theta under the distribution Q of x given theta, evaluated using a training set. So you essentially have some probability model saying that the likelihood of a parameter, the likelihood of the parameter for some training, for x is this function, and now you're just maximizing that, which is the logarithm of that, which is just maximum likelihood estimation, basically. So we said minimizing the Kullback-Leibler divergence is equivalent to maximizing the likelihood function. So I think a really nice connection between maximum likelihood and minimizing KL distance, showing that they're basically the same. So that is a interesting chunk just all by itself. And now finally we come to the last important concept that's going to be introduced, which is the concept of mutual information relating to random variables. And so the idea here is that if two variables are unrelated, well, unrelated means they're independent. So we can consider their joint probability distribution, and if they're unrelated, that means the joint probability distribution is the product of the marginal distributions. And so then all we do is, well, then our notion of relationship can just be the KL divergence between the joint distribution and the joint distribution when we assume independence. If that is non-zero, that means they must be dependent somehow. And this will capture all kinds of dependence, not just linear dependence, but any kind of dependence, because we're looking at the full joint distribution. So let's have a read. So consider the joint distribution between two sets of variables x and y given by p of xy, what we just said. Now, if the sets of variables are independent, then their joint distribution will factorize into the product of their marginal. So p of xy is equal to p of x times p of y. So let me just highlight that because that is important. Sets of variables are independent, then their joint distribution will factorize the product of their marginals. Okay, if the variables are not independent, we can gain some idea of whether they're close to being independent by considering the Kullback-Leibler divergence between the joint distribution and the product of the marginals, given by, and check this out, what do we have here? It's the KL between, so this is the true distribution, and now you're going to assume your approximating distribution is going to be the one where you assume they're independent. You kind of factorize them into x and y. And now this quantity that we just defined is called the mutual information between x and y. So this is a really important quantity that captures any dependence between them. And we know because of the KL divergence that it's greater than or equal to 0 with equality if and only if x and y are independent. And the reason, so that's coming in because remember the KL divergence is equal to 0 if and only if the two probability distributions are the same. So that means that p of xy equals p of x times p of y. So the joint distribution is a product of the marginals, meaning that the two variables are independent. And now it's very easy to show, so I'll leave that as an exercise for you. Using the sum and product rules of probability, we see that the mutual information is related to the conditional entropy through these expressions. These are actually quite intuitive expressions, and actually these are the ways that I remember what mutual information is. And they actually has a very intuitive meaning. So it says that the mutual information between x and y, this is kind of the uncertainty about x. This is just, if you don't know anything about y, how uncertain you are about x. And now this is, the uncertainty about x if you know y. Right? So it says, how uncertain are you to begin with about the variable x, and then how uncertain are you when I tell you y, on average, and just subtracting those two. Now, so if x and y are independent, then knowing y won't tell you anything about x. So your uncertainty in that case will be equal in both settings. So your mutual information will be 0. But if there's any kind of dependence between them, then the conditional entropy, so the uncertainty you'll have after I tell you about y, will be smaller than the uncertainty before I tell you about it, before I tell you about y, on average. And so this quantity will be positive, telling you that there is some dependence. It doesn't tell you the form, but there is some dependence between the two variables. So very useful measure of independence, although it can be difficult to compute. These entropies require doing these integrals, so it can be hard to compute, but very useful. Another very useful property is the symmetry aspect. So so what I mean is, if you look at h of x minus h of x given y, well, it's the same as h of y minus h of y given x. You can just go back to this definition and see that it's kind of symmetric in terms of x and y's. You can just swap them around, and it doesn't make a difference to the value. And so the reason why that's important is that in some settings it can be actually much easier to compute the entropy, on one set of variables than on the other set of variables. So and so it's really useful that actually the mutual information doesn't matter which variable you use. It's the same in both directions. So that's something worth keeping in mind. Okay, so thus we can view the mutual information as a reduction on the uncertainty about x by virtue of being told the value of y or vice versa. And now there's kind of the nice Bayesian perspective. We can view p of x as a prior distribution for x and p of x given y as a posterior distribution after we observed a new data y. The mutual information therefore represents the reduction in uncertainty about x as a consequence of the new observation y. So kind of a very natural interpretation of the mutual information. Great. So so this is kind of really important, a very important and very useful concept. And actually, even if you can't compute it numerically, it's often really, I found it very useful for kind of organizing my thinking about the relationships between different sets of random variables. So definitely worth knowing. I expect we'll come across both mutual information and certainly Kullback-Leibler divergence many times throughout. So you'll get lots of practice and intuition building with them. But yeah, really worth knowing, and just worth getting comfortable with. Good. So hopefully that was useful. In the next lecture, I will just go and prove this property about Kullback-Leibler divergence being positive. I think it just needs its own little page to discuss. But yeah, I think that's about it. That was kind of quite an intense last section. This whole chapter, part of the chapter, seems to be kind of a crash course in information theory. It's obviously an enormous topic, but I guess this is just covering the bits we need. So hope you liked it. Let me know. Let me know if you did. Let me know if you didn't. If you of course, if you catch a mistake, let me know, and I will gladly fix it. We'll all learn better that way. But yeah, hopefully that was useful, and that I will see you in the next lecture. Thanks.